true. So it will. This will return true. This will leave. I think the way this works is, it'll replace the values on the stack with a true value. So it replaces this with 1. So now there's nothing else. It takes those values away. If they had not been equal, 7, 5, 7, 4, whatever, it will replace it with false, which is actually a blank value. So 0 is just blank. So if it was false, it would just be replaced with, an empty value, which is false. So that's the simplest possible script I could imagine running. And there are a few extra complications that you see in real scripts that get executed in a real transaction. So the difference is, so that was one simple script. Let's suppose you actually have a script sig and a script pub key. So let's do another thing that's slightly different. Let's suppose my script sig is the simplest possible thing. Again, I push 2 bytes to the stack. I push 7474. And this is my script sig. And then my script pub key is to push, same thing, 7474, and then op equal verify. What this does is, first, the script interpreter will evaluate script sig. That pushes 1 value to the stack. Now, it's done executing that, and there's nothing false on the stack. There's a true value here, 7474. Nothing has returned. The transaction is not invalid or anything. So it then leaves the stack the same and begins executing the script pub key, which pushes another value, and exactly the same as before. It has the same value there. So when op equal verify runs, it confirms that they are equal and replaces it with a 1. So it pops values and pushes a new value. So when I say pop and push, that's what I mean. It pops those values off, pushes another value. So you would never see this in a real transaction. So let's suppose this occurred for there's a transaction, and these are, I took the script, sig here is from a real transaction. You would never ever see this, because let's suppose you paid to a value that says your script pub key pushes this value to the stack and then runs op equal verify. Well, anybody would know as soon as you look at the script that this script to spin this would be just to push the same value to the stack, and that's it. That's how you would spin it. So there's no private key or signature involved here. This would be a trivially, you could create a transaction like this that sends it to a script that could, return true that anybody could spin, right? Anybody would be able to figure that out. So if you ever created a transaction like that, there's probably somebody running a bot right now that looks for transactions like this that would be immediately spent. So, does that make sense why that would not be secure? So, the solution to the problem of security is adding signatures. So we can sign data and then require that the proper signature be present. So here's now let's suppose we've got a real transaction here, which this time the input is, this time we have the original transaction that pays 2. So this has, this has the opt-up, whatever. This is a real Bitcoin address. And now I try to spend that money, and I have, in here is another script. And this is, so now what I'm going to try and do is I'm going to try and validate a actual Bitcoin transaction. I take the script sig, exactly as I did before, except this time, what the script does is it pushes an actual signature to the stack, and it pushes an actual public key to the stack. And the script pub key pushes this so the script pub key is a thing that sort of had the address in it, and it pushes, let's see if I can remember this, it's opt-up, op hash 160, Then it pushes the address, right, the hash of the public key. Then it does op equal verify. Yeah, op equal verify. And then op check sig. Okay, so the difference is this time, rather than put some fake, like in my earlier insecure transaction, I pushed some script that anybody would be able to spend. It doesn't require a special private key. This time I push a hash of an address here, and then in my script pub key, I require that a signature be checked. So I require that I hash that there be a public key that is present, and that I hash it, and that it is equal to the address, and that's what the op equal verify means, and then I check the actual signature. Okay, does all this make sense? This was not prepared, but this is like, so, and I'm not drawing out the stack just because drawing out this all by hand is just cumbersome, but like what this means is, the script sig gets executed first, signature gets pushed to the stack, so now the stack consists of a signature. Now I push the public key to the stack, there's a public key on top. Nothing false has happened, the transaction has not been invalidated, the stack stays the same, then the script pub key gets executed, it duplicates the top item on the stack, which is the public key, so there are now two public keys. Then it hashes the top item on the stack. If I did, yeah. I might have, did I do this backwards?
No, that's too right.
No, this is right, yeah. Then I hash it, and it places the hash, yeah, that's right. It hashes it, then it adds the hash, because I also have the hash here to the top. So now there are two hashes. Then it runs op equal verify, confirms that the two hashes are equal, pops them, and then all that's left is a public key and a script and a signature, and then op check sig actually checks that the signature signs the transaction. One thing I thought about making was like, there should be like a graphical one of this, because this could definitely be like, you could see it, like, if you could just see like the stack things being added to it, it would be very explanatory.
So right now, whenever we submit a transaction, do we need to like if we don't use Block or BlockchainIU's API system like APIs, do we need to do all this by ourselves? Like actually write the scripts or?
So if you run a full node, you are doing it by yourself, right? These scripts get executed if you just download and run Bitcoin Core, you log on to the Bitcoin network, you're connected, you receive transactions. If you validate a transaction, what you're doing is you validate every single input to the transaction. So if there's more, you run every single script. So if the way most people do this is, like if you use a normal web wallet, you're probably not running any type of verification software on your computer. If you use some type of service, especially if you use like Coinbase or something, Coinbase, nothing runs on your computer. They do everything on their side. If you run something a little bit more sophisticated, you might do the signing on your computer. You hold the private keys and you sign it, but you're still not running any scripts. The only way you need to run the scripts is if you're actually validating that a transaction is valid, which is validating the entire blockchain.
But when I send a transaction, I don't need to build all of this, right? If I'm using some APIs or something.
No. If you want to, like, here's a great example. The Trezor. You guys know what the Trezor is. It's a hardware wallet. It's a very simple piece of hardware. And the way that the idea of a Trezor is that it's a piece of hardware that holds your private keys. So if your computer, gets compromised, the private keys are not being held on your computer, so nobody can steal your money. So the private keys are on a little device, and all the little device does is it signs data. And all it has to do is it produces the signature. It doesn't have to run any validation. It doesn't have to have the entire blockchain. It has the cryptography on it. It's got elliptic curve math on it so that it can create the signature. But that's all it does. It signs the transaction and sends the signature back offline. So to create a transaction, you don't need to do any of this. You do, however, need to do one somewhat complicated thing, another thing I'm sort of glossing over, which is the right way to hash a transaction. You have to be signed, has to be done exactly correctly, because when you validate a signature, you hash the transaction, you better be using exactly the same hash or people are going to think it's invalid. So there's one extra subtle stage, which is correctly hashing a transaction, which is not trivial because you have to blank out the input scripts in exactly the right way. Because the thing you're signing is the thing that has the signatures in it. So you have to remove the piece of data that will hold the signatures. Otherwise you can't sign the signature itself. So there's a right way to do this, and it's called I think it's just called signature hash in Bitcoin Core. And there are 3 different ways, I guess there are actually like 6 different ways to hash a transaction that are distinct and have to be done in byte for byte correctly. So the Trezor has to do that. That's it, and sign it. So it doesn't have to run any validation. But yeah, if you want to validate the blockchain, which you do if you run a full node, that's when you run all this stuff. And this is so, in order to validate like a block, you have to validate all the transactions. So you run all these scripts, but there are other checks as well. So it's not just this. You also have to check things like the max block size. So not only do the transactions have to be valid, but the block has to be valid. So the block has to not be greater than 1 megabyte. So there are a bunch of other checks. And so this is why it's sort of not recommended that you try and write a full node. You should just run Bitcoin Core, because unless you are completely perfect and get all the checks exactly correct, you might get one thing wrong and then you go off on a fork, So yeah, you have to get all the checks exactly right, and it's hard to do it. And I don't think anybody's ever successfully done it. Like all the alternative implementations of Bitcoin, one of the core developers, Peter Todd, sort of goes out of his way to figure out how the other implementations are flawed. So he's found a number of flaws in other implementations where he gives them a specially constructed transaction that sends them off on a fork. They think, like, he'll do something like create a transaction that goes in an actual block. That's a valid transaction according to Bitcoin Core, but this alternative implementation thinks it's invalid, just because of some obscure detail somewhere that the programmer writing the alternative implementation did not get exactly correct. So it's hard to get all the details right.
Hey guys, Solomon has some slides. I don't know if there's still more questions about that. He has some slides that we could show, or you could just ask this even later on. We can share them on the Reddit. So if there's more questions.
So I guess because you were mentioning there's a graphical way, right? And there's just some way to, so those are some graphics for the stack.
I would just like to see like, because exactly, I would like to see graphics of the stack. Something like a script interpreter that shows the graphics.
So kind of like showing the script in the
Exactly this. Yeah, we should put this on the screen.
And then just show it like how it changes.
Yeah, exactly. This is perfect.
Can we, for a small fee?
Yeah, do you?
Thanks to Solomon Wu. I can't promise you what's on here.
It's a Trojan horse.
Oh, it's not Trojan. We need it.
So yeah, so this is just like, what is it on?